Let's talk about MRI magnetism as a fundamental fact of nuclear magnetic resonance imaging. The atom is the basis for all living things. It is a building block. Understanding the atom is the key to learning MRI, magnetic resonance imaging. The atom is created from charged particles. The electron has a negative charge, the proton a positive charge, and the neutron a neutral or no charge. Electrons orbit the atom itself, or the nucleus of the atom, and the nucleus of the atom is composed of protons and neutrons. All the recognized molecular elements that we utilize in science are created from the atom. This includes us as human beings. Magnetic resonance imaging is a diagnostic imaging test that uses a homogeneous magnetic field and pulses of radio waves to create images of structures and tissue. Images are created by disturbing a stable magnetic field with radio frequency pulses. The interaction of the energy pulses to the homogenetic field is recorded to create data. This data is used with imaging algorithms to create visual images of tissue. Here we can see an MRI image of the chest and cardiac area. A medical image is a snapshot of specific interactions of energy to a targeted anatomy for a specific moment in time. Humans are composed of atoms, and we are three-dimensional creatures, so we need to record the atoms in all dimensions. To do this, we must capture, store, and recreate the data in all three dimensions: axial, sagittal, and coronal. This is called the Cartesian coordinate system. The stored image data can be used to create different types of images. The atom is the fundamental building block for all things in this universe. The original name for what we call MRI today was nuclear magnetic resonance imaging. Since the term nuclear had a negative connotation, it was deleted from the name. This simple change to de-emphasize the term nuclear in the name transformed how many people understand the physics of. Remember, the atom is characterized by its nucleus with protons and neutrons and the orbiting electrons. It is the sum total of what the atom is made of neutrons, protons, and electrons that make up the combination of atoms into a molecule, and molecules are the basis for tissue. For instance, the human body is made up of about 6% inorganic compound, 24% organic compounds, and 70% water. How do we determine if it's organic or inorganic or water? We look at the formula of the number of neutrons and protons in the nucleus. So we have H2O. The electrons will correlate to what is in the nucleus. Let's look at the ingredients in the human body. We can see that we have 65% of the body being oxygen, and about 18.5% being carbon, with 9.5% being hydrogen, and 3.3% being nitrogen. The hydrogen atom is the most abundant element in all of the universe. It is given the number 1 in the elemental table. It is composed of 1 proton and 1 electron. Nuclear magnetic resonance imaging uses electromagnetism and RF energy pulse sequences to create images. Molecular elements with even mass numbers positive and negative, cancel each other out, and therefore there is no charge. Odd-numbered elements possess a charge, and therefore they have the property of spin, or quantum spin. Thus, we can use them in magnetic resonance imaging. Remember, we want to measure or image human tissue and organs. In the levels of cellular organization, the atom, the molecule, and the organelle all are below the cell, which creates the tissue and the organs that we wish to visualize. After we look at the tissues and organs, we can diagnose the organ system and the organism, which would be the human being. This is why we state that the atom is the building block for all things. An electron that is spinning creates magnetism. Aligning hydrogen protons within a magnetic field creates spin-spin. The proton is spinning and the electron is spinning, but they are spinning at orthogonal angles. A magnetic field always has two poles, with the stronger pole being the north pole, so that the magnetic flux or lines goes from north to south. The north pole is stronger because at any given moment in time there are more protons in the north pole than there are in the south. If the numbers were equal, they would cancel out. There are three different types of magnets used to create MRI images. They are a permanent magnet, resistive magnets, and superconductive magnets. The permanent magnet is something like lodestone, wherein electrons spin in an element. The other two magnets, a resistive and superconductive magnets, are coils of wire in which the electrons travel. The permanent magnet is a material that can create a magnet itself, or a magnetic field by itself, without any external help. They are very low in power, from about 0.15 to 0.4 Tesla maximum. A resistive magnet is made from many coils of wire that are wrapped around a cylinder through which an electric current is passed. This generates a magnetic field. Resistive or air core MRI magnets operate at room temperature using standard conductors such as copper in the shape of a solenoid or a Helmholtz pair coil. A solenoid is a cylindrical shaped coil of wire. With a standard conductor for a wire, it takes a great deal of electricity to move the electrons through the wire because of impedance or resistance. A special type of material using niobium alloy is used in superconductive magnets. These wires are cooled by liquid nitrogen to about 10 degrees Kelvin, or 4 degrees Kelvin would be absolutely perfect. But the idea here is to reduce the impedance to almost zero, and this allows the electrons to move freely with no impedance, so we don't have to have electricity pushing the electrons. Once they're in motion, they just keep going. This is why superconductive magnets are always on. They're never turned off. Superconductive MRI magnets use a solenoid-shaped coil made of alloys such as niobium, titanium, or niobium and tin surrounded by copper. These alloys have the property of zero resistance to electrical current when cooled to about 10 degrees Kelvin. Let's take a look at a superconductive MRI scanner. Notice that we have the main field magnet or coil, it is surrounded by gradient coils. Gradient coils are secondary coils that are added to the main field of magnetism to create X, Y, and Z fields of magnetism. These are then surrounded by radio frequency coils. Radio frequency coils are what are used to create pulse frequencies, which turn on and off the gradient coils. Magnetic resonance imaging uses electromagnetism. When we discuss magnetism in MRI, we're talking about fields. In quantum physics, fields are created from spins. A spin can only be up or down. In a field, a charged particle that spins creates a magnetic field. So let's talk about putting the magnetism in the MRI. First, we need to look at the two orthogonal waves. One is an electric field and the other is a magnetic field. The wave travels in the Z direction. Note the propagation direction, or the direction of the Z, is also the electric field and magnetic field direction. At the top we can see a sine wave, which gives us the wavelength or frequency in a two-dimensional direction. Whereas below we can see the combinations of both the electronic field vibration and the magnetic field vibration in 3 dimensions. Now that we've discussed magnetism and fields, let's take a look at a superconductive magnet. Here we have a cutaway view of the superconductive magnet, below which we have a representation of Faraday's law of induction. This is a demonstration of how a coil of wire having a magnet passing through it can cause electrical current to flow. Next, we see pictures of a superconducting magnet with an aluminum former. The windings here have been broken up into 8 sections. This improves homogeneity and minimizes fringe fields. Here we have a representation of a GE MRI system. It is a cutaway and shows the patient inside of the main magnet. It also shows the gradient coils and the radio frequency coils. The patient lies inside the magnet and their whole body is magnetized to one specific level. In other words, all the hydrogen atoms are at the same magnetization. Once the body is magnetized in the primary field, we then superimpose a second magnetic field in the X or Y or Z coordinates. This allows us to superimpose all the gradients and thereby map the body for tissue and structure. Here we see a representation of mapping the structure and creating T1 and T2 images. So now we've seen how the body has been magnetized and mapped using gradient echoes. Let's now look at the addition of the pulse sequence to be able to gather the data we need for our images. Here we see a representation of a spin echo pulse sequence. Hydrogen protons are aligned along the longitudinal axis of the MRI. It is a stable magnetic field, and there is no current produced. Here we can see that the magnetic energy flows in a circular pattern from the strongest pole, which is the north, through the lesser pole, which is the south. All three spin components along the x, y, and z axis may rotate into our 3D space for an electron in motion to create the north-south magnetic field. This is known as spin-spin of the electron components as they spin in and around the main magnetic field. Again, energy created by the spin of the electron in orbit creates a magnetic field for that electron, but that electron also spins around the main magnetic field. So we have spin-spin. Magnets always have a north and a south pole. If you break a magnet in half, you just have two smaller magnets with a north and a south pole. So let's look at the laws of magnets for attraction and repulsion. An invisible force or energy occurs when there is attraction between a north and a south pole. Conversely, when we have a similar pole, there is repulsion. And you can see how the electron filings in these images have moved away during repulsion and have joined during attraction. Let's see what happens when we actually use a radio frequency pulse to disturb this invisible force, whether it is attraction or repulsion. Here we see a spin echo RF pulse, and we can see how we are able to record the energy changes once we disturb the static magnetic field. Here you can see T1 and T2 images being produced by utilizing a 90 and 180 degree pulse sequence and recording the echoes from these pulses. We are going to go in our next module and look at both spin echo and gradient pulses. There are many pulse sequences that are utilized in MRI imaging and combinations of pulse sequences. We're going to study in the next module the spin echo pulse sequence, and we will also take a look at gradient pulse sequences.